Okay. So where does it start? It starts at 0.25 and it ends at 2150. Okay. So we can kind of see that, right? So you read a graph the way you read a book, so from left to right. So on the left side, where would we put that L at? Well, on the left, and then the R goes on the right. So on the left side, you want to put a boundary that's touching your graph, but not cutting it. So this number right here, it's cutting at 0, right? Because you want your X values. So your left bound is at 0, and then your right bound, it's not perfect, but it's supposed to be at 20. So 20, which you will notice they're the X values on where it starts and where it ends, right? 0, 20, 0, 20. Okay, so at the 0, you can see that the graph has a solid dot, so that's equal to, and at the 20, it has a solid dot, so that's equal to. So they both have an equal to. So your domain is from 0 to 20, all real numbers from 0 to 20. Now, for your range is RY, which means all Y values. Now, I need y'all to get used to understanding that f of x is the same as y, right? So f of x equals y. So sometimes in your multiple choice, instead of a y, you're going to see f of x. You need to know that that just means y. Okay, so we have f of x, which is my y, is between, well, your y-axis travels up and down. So that means it goes from bottom. So I'm going to put my b at the bottom and my t at the top. So you want a boundary at the bottom and you want a boundary at the top. So if I were to cut this at the bottom, you want your boundary to be, that's a really thick line. Hold on. Here, let me do it this way. Okay. You want your boundary to be at the bottom of your graph without cutting it. It's, that number is at 25. Then you go to the top and you do the same thing. So that boundary at the top is at 150, which you will notice is the Y values of where it started and where it ended for this example. Okay, and then obviously our Y-intercept is at 0, 25, or you could just write it as 25, right? Or Y equals 25, same thing. Okay, now, today we are covering exponential key features. Okay, so we did exponential functions a while back ago, like, I don't know, first semester, first 6 weeks or something like that. So we're pretty much bringing it back up, but now we're going to go a little deeper into it. So the thing I want to focus on now is the fact that we have domain and range. So you will notice that it says domain is all real numbers. Keep in mind that in Algebra 1, we're being really shallow with what we're covering with exponentials. So we're barely at the surface, okay? So we're literally just doing basics right now. So we know that your domain is all real numbers, and it doesn't matter if it's a growth function or a decay function. What matters is the fact that we have the arrows on the left and the right. So you will notice that in our warm-up, I gave you an exponential function with endpoints, right? Which is the reason why you have values. You have a left, a right, a bottom, and a top bound. So you were able to contain that graph in a box. If I look at the little rough drafts we drew here, right? They both have arrows on the left and the right, which means that you cannot stop it, you cannot bound it. There is no limit to how far left and how far to the right it can go, which is why the domain is all real numbers. Now, for your range, you have all real numbers greater than 0. So the reason it's greater than 0 is because of a horizontal asymptote. So remember, it's been a good minute since we've done this, right? So if I look at this picture, and if you look at this pink dashed line that I'm drawing, right? With that right there would be your horizontal asymptote. So that graph looks like it's sitting on there, but it's actually not. So if you think about how we talked about it at the beginning of the year, we said that exponential functions are pretty much like a booty, right? So you're about to sit on the porta potty, but do you actually want to touch the porta potty? No, because that's gross, right? There might be Rona on that seat and you don't want Rona on your butt, okay? So you have like, imagine the toilet, right? You don't want to actually touch it. It may look like you're going to touch it. You may get really, 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 really close to touching it, but do you actually want to touch it? No. So that is your horizontal asymptote. It is like that invisible line that is stopping you from actually touching the toilet or whatever you're trying to sit on. Okay. So that's your horizontal asymptote, right? So that is that line, which is the description of the ending behavior of a graph as it approaches a value. All right. So that's your brief summary, and then we're gonna get into the chart and we'll talk more. Now, a very important skill that you learned, according to last period, it was like sixth grade, I think, I don't know. When did you learn how to convert percentages into a decimal? Do y'all remember? Like sixth grade-ish? Okay. So that's a skill you're gonna need today. So we're going to review it real quick just to make sure that everyone remembers how to convert a percent into a decimal. Okay, so on the side, I went on ahead and put what you do, right? So all you have to do is move decimal 2 spaces to the left. So you have the percentage of 50. So we have 50%. I don't see a decimal. So if you don't see a decimal, that means that the decimal exists to the right of that number, right? So then all you have to do is move it 2 to the left. So we're gonna go this way, 2 spaces, 1, 2, which means 50% can be converted to a decimal as 0.5 or 0.50, right? That 0 is irrelevant in this situation. So you could keep it or you could not. So now go on ahead and convert 30% into a decimal and type it in the chat. Good so far? Okay. Yes, we would end up with 0.3 or 0.30. A lot of you put 0.30, some of you put 0.3. Both of them are correct. So now let's go on to the next one. So we have 4%. Again, I don't see a decimal, so I know my decimal has to exist at the very end of that on the right side. Same process. We're going to move it 2 to the left. 1, 2. So my dot's going to go right there, and I see an empty space. So any empty spaces, I'm going to put a 0. So my 4% converted as a decimal is 0.04. Go on ahead and do 8%. I'm going to give you about 10 seconds. Go on ahead and type it in the chat. Good. Perfect. Good. Okay, so good job. That would be 0.08. Last one, we can see that, or second to last, we have a decimal, right? So I don't have to make one, or I don't have to put it there because it's already there. But the rule does not change. You're still going to move it 2 to the left. Good, thank you for that. 1, 2. Include in your zeros, so 0.025. Go on ahead and do the last one, 10 seconds. All right, so for the last one, you already see a decimal, so you're gonna go 1, 2. This time you have 2 empty spaces, so you're gonna fill in 2 zeros. So 0.0025, there you go. Okay, so we all feel refreshed on how to convert percentages into a decimal, okay? So now, moving on, you're gonna need this for the lesson later on. So we're gonna talk about this beautiful chart I made for y'all. This pretty much has all the information you need to know about exponential growth and decay functions, okay? So we're gonna start with the graph because I wanna talk about that visual part, which is why I need y'all to have these pre-done, pre-written, because it doesn't mean I'm gonna go in the exact same order. I need to know that I can jump around, okay? So you have to have these pre-written. So I'm gonna start with the graph. So looking at this graph, I want you to know, so remember, on the left side, I have growth versus the right side is decay. So on the left side, right, where we have growth, we can see, remember, you read a graph. So, okay, yeah. So we read a graph the same way we read a book, left to right. So if you look at both of these, left to right, on the left side, we see that it's starting low and then it's growing to the right. So that is increasing, right? So then that's how you know it is decay, because it's increasing left to right. Then on the right side, you can see that it's starting high, right? So we can see that it's starting high. And then from left to right, it's decreasing, which is what makes it decay. Just how we have linear functions, right? So if it's going this way, it's a positive slope because it's going up left to right. And if you have a negative slope, right, it's go from left to right, it's going down. Same concept. So now notice that for both of these, I went on ahead and put the domain and range again, but I'm hoping that because there is a visual, it makes a little bit more sense as to why the domain is all real numbers. And we can see that we have an arrow to the left and an arrow to the right on both of these. So they're gonna go forever to the left and the right. So the domain is always going to be all real numbers, as long as you have arrows on both ends. On the warm-up, you should have seen, or hopefully you notice that that is also an exponential, right? It's curving a little bit, but there's no arrows. I gave you endpoints, which tells you that it has to start and end somewhere. So if they have arrows on the left and the right, then you have to understand that the domain is all real numbers, which means it's never gonna stop. All real numbers means it's going to cover everything, all real numbers, right? The word all means everything, inclusive of all. Okay, now you're also gonna notice that for the range, we have the exact same thing for both of them. Why is that? Well, if you look at both of these graphs and you look at the horizontal asymptote on both of them, right? This pink dashed line that I drew, your graph is above the pink line. So above means greater, bigger, which is why we have y is greater than 0 on both of them, because of that horizontal asymptote. And that graph exists above the horizontal asymptote. Okay, now, hold on, let me. There we go. Okay, so now the second thing you may or may not be wondering is, why is there not an equal to? Okay, yes. Hold on. All right, so where was I at? Okay, so you're gonna notice that for the range, both of them are missing an equal to. Well, why is that? If we go back to our porta potty analogy, do we actually ever touch the toilet? No, right? So if you don't touch the toilet, does the toilet ever equal you, right? If you think about it in that aspect, you never equal the toilet, right? You don't touch it. So because you and the toilet never touch, then you can't have an equal to symbol, because you're gonna hover over the asymptote. You're never actually going to touch it or cross it as it keeps going to infinity, okay? So that is the reason why there's no equal to. Now, the next thing we're going to look at is we're gonna come up here and we're gonna look at the equations of both of these. Now remember, on the left we have growth and on the right we have decay. The thing that you're gonna see that they both have in common is the fact that they both have an A, right? And notice that your A is in the front for both of them. And your A is your y-intercept, which is your initial value, which is where it starts, okay? So before we keep going with this, I want us to talk about, let's refresh our memory and let's talk about y equals mx plus b, right? So this is a linear function. What do we know about linear functions? Well, we know that our m is our slope, right? And how do I know where my slope is always at? Because it has what next to it? The x. So it's very similar to exponential functions. So I know that my slope is always next to the x and my y-intercept is always by itself without the x. So if you look at our equations for growth and decay, you should also notice that your a, what we call the y-intercept, does not have the x. Do we all see that, right? Just like linear functions. You're also going to notice that we have this b, right, for both of them. And they both have the x as their exponent, which is why that one is your factor. Remember, factor means to multiply. So you're going to multiply that b by itself x many times. So your factor is the one with the x, just how your slope is the one with the x. And your y-intercept is the one without it, okay? So if it has an exponent of an x, it is automatically your factor. So why do I say that? Because sometimes I can give you an example that looks like this. So what if I give you y equals 3 times 2 to the x? This is easy, right? You can clearly tell that this one has the x, so this has to be your factor, and this one has to be your y-intercept. That's very straightforward. But if I give you y equals 2 to the x, does that mean that 2 is your y-intercept because you see it first? No, that's not what that means. This one has your x, so this has to be your factor, which means that you are multiplying it by an invisible 1. So your y-intercept here would be 1. Okay, so that's why I tell you, if it has the exponent of an x, it has to be your factor. Just how linear functions, if it has the x, it has to be a slope. That number in front of it has to be your slope. Okay, now we've talked about what's your y-intercept. We've talked about how you know that's your factor. Now we need to talk about how do you know if it's a growth factor or a decay factor. On the chart, I'm giving you factor is bigger than 1. So basically, any number bigger than 1, it is automatically growth. It doesn't matter what number, okay? It could be 1.000001. Because of that 0.00001, it is growing. 1.1, growing. 1.2, growing. 1.3, growing. 2, 3, 4, 5. Anything bigger than 1 is automatically growing. Now, so if anything bigger than 1 is growing, then how do I know it's decay? Well, you're decaying if it's between 0 and 1. Well, what does that mean? That means 0 point something. I do not care what the something is. If you have a 0, then the decimal, it is automatically decay, okay? Now, when we're looking at these things, I don't want you to get confused between fractions. Just because it's a fraction does not automatically make it decay. So let's look at an example of that, right? So if I give you an example of, let's do the same one I've been doing. 3/4 and 4/3. Those are both fractions. So does that mean that both of them represent a decay exponential function? No. 3/4 is the same as 0.75, which you can see is 0 point something, right? So this would be decay because of the 0 point something. But if you look at 4/3, this is equal to 1.333 repeating over and over again. This is not 0 point something. This is bigger than 1. So this one would actually be growth. So you need to make sure that if you are given a fraction, you convert it to a decimal to verify if it is growth or if it is decay. Okay. So now after talking about the equation, now let's look at a table. Okay. So again, right now, I'm just trying to point out things that are a lot more logical, right? And kind of common sense so that when you're looking at it, you're like, oh, well, yeah, duh, that makes sense, right? So if you're looking at a table and its growth, do we see what our y values are doing? It's going from 2 to 4 to 8 to 16. What is happening? Are those y values growing or decaying? Growing. So it makes sense for this to be a growth table, right? Now, also, I'm just pointing out what the y value looks like, right? So, or what the y-intercept looks like at 0, 2. Now, to find your factor from a table, that's where you need to, because we know that exponential functions are multiplying, right? Then to find your growth and decay factor, you just need to do the inverse of that, which is divide. So you're always going to choose a number and divide by the one before it. So we have 4 divided by 2. Then we have 8 divided by 4. And then here we have 16 divided by 8. So 4 over 2 is the same as 8 over 4, which is equal to 16 over 8, which all of these are directly proportional, which is 2. 4 divided by 2 is 2. 8 divided by 4 is 2. 16 divided by 8 is 2. So your growth factor is 2. And if you go back and remember, if you're having a growth function, then you know your factor has to be bigger than 1. 2 is definitely bigger than 1. So you know that has to be your factor, right? So let's say you divide wrong. Let's say you do 2 divided by 4 instead of 4 divided by 2. Well, 2 divided by 4 is 1/2. 1/2 is 0.5. So that should be your automatic stop and be like, wait, 0.5 is decay. This is growing, so that cannot be correct, okay? So it's those little things that's gonna help you figure out right versus wrong. So if we look at the right side for your decay, same process. To figure out the factor, you're gonna do the exact same thing. And that is grab your two numbers. So we're gonna grab the 50 and divide by the one before it, which is 100. Then 25 divided by 50. And then for the last one, 12.5 divided by 25. Well, what do we notice? 50 is half of 100, 25 is half of 50, 12.5 is half of 25. So our factor here is 1/2. So you can write a decay factor of 1/2 or 0.5, right? If you write it as a decimal. So then this is where you would stop and look at it and say like, okay, it's 0.5. I think this is decay because it's going from 100 to 50 to 25. It is decreasing. So I know it has to be decay. So this is 0 point something, right? Yes, it is 0 point something. It's 0.5. So it makes sense. That tells me that I probably calculated my factor correctly because everything is making sense. I'm making sure to look back and make sure that everything looks right. Because if you accidentally divided incorrectly, you would have done 100 divided by 50. Well, 100 divided by 50 is 2. 2 is not a decay factor. 2 would be growth. So that would be your indication that, hey, I divided something wrong. Okay, so we've looked at the equation. We've looked at tables. We've already talked about the graphs. Now we're going to talk about what happens when you have application problems. This does not mean that it's automatically word problems, but more than likely it's going to be word problems. Now, you know that you need to use these equations if they give you a rate, which means they give you a percentage. If they give you a percentage, then that is your big, huge red flag or green flag. I don't know how you would look at that, but it's a flag telling you, hey, you need to use these equations. Okay, so let's analyze these equations before we go to the examples. So we have, For both of them, you're going to notice that you still have your y-intercept, right? That hasn't changed. Whatever your initial or starting value is, that's always going to go there. Now, what you are going to notice is that I didn't give you a b this time. It's still there, but now I'm showing you where the b comes from. So up here, you can see, so let me highlight this real quick. You can see that I wrote growth factor there. That means that your b comes from 1 plus r. And then on the other side, you're going to notice that I put decay factor over the whole thing in parentheses, which is 1 minus r. Okay, so one of the things that we wonder a lot of the time is what in the world does the 1 even mean? Okay, so remember, a skill that we practiced at the beginning was converting percentages into decimals. So what that means is that we have 100%. Well, what does that mean? If I convert 100% to a decimal, what does that give me? I put a dot here, I move it 1, 2 to the left, which means my dot goes there. So what am I left with? A 1, which is where this 1 is coming from. So this 1 is representing 100%. Okay, so here's the way, okay, so here's the difference between linears and exponentials. Here's the best way for me to explain it. So even those of you that are writing notes, listen to me. Okay, which I know you are already, but whatever. Okay, so for example, we have Rona, right? We have this COVID thing that I like to call Rona because she's such a Rona. Okay. So where did Rona start? Rona started in China somewhere, according to all the news, right? And Rona started with one person that we're just going to call her Rona because that's what I call COVID anyway. I call her Rona. Okay. This one person was my population of who had COVID, right? 100% of my population was one person, and that one person was the only one who had the virus or whatever. Well, then what happened with that one person? That one person was with their family, let's say 4 people. That one person gave it to 4 people. So how many people have Rona now? 5. So what can you tell me about my population? 100% of my population is what now? 5. Okay. So an exponential function is basically regrouping after you do something. A linear function can start at 1, right? And let's say this disease was linear, then that means, let's say 5 people get sick every day. Only 5, that's it. So if we have 1,000 people sick, how many people are going to get sick? 5. That's 1,005 people. The next day would be 1,010 people. The next day would be 1,015 people. Do you see how that's growing consistently, right? For every 5 people. With an exponential function, you're grabbing your percentage of people. So for example, once we reached 500 people, right? If we double that, that's 1,000 people. 1,000 people, let's say there's 1,000 people in this world with Rona, which we know it's way more than that. But at one point, we only had 1,000 people, right? 1,000 people, you double that. If each person can spreads it to one other person, that's 2,000 people now. So what's your new population? Is your population still 1,000? No, your new 100% is 2,000 now. So now you're going to grab those 2,000, and those 2,000 people are going to spread it to another 2,000 people. So what is your new population now? Now we're at 4,000. 4,000 spread it to another 4,000. 4,000 is now turned into 8,000. 8,000 would turn into 16,000. 16,000 would turn into 32. Do we see how quickly that's growing? That is why, if you hear the news carefully, a lot of the times people refer to the virus as an exponentially. They'll tell you it's growing exponentially. That word exponential comes from this function because it is growing at an exponential rate, which is an exponential function. Because of this 1 right there, right? That 1 is representing your percentage, your group as a whole, and that can change. So instead of saying, oh yeah, we're at 25 and we're only going to grow 10 people each day, no matter where you come from, you're only going to grow 10. With exponential functions, you have a certain percentage, which is 100% of your population, right, that we're observing or looking at. And that quantity is just going to keep doubling or tripling or growing at whatever rate it chooses. Oh man. Hold on, let me share my screen again. Okay, so right here, when you're looking at these equations, when you're talking about rates and the rates are given, if you look at the growth side, right? If you're growing something, it obviously makes sense to be adding something, right? Growing means to add. If something is decaying, then obviously it's losing something, so you would be subtracting. So the first thing we need to acknowledge is the common sense behind the adding and the subtracting, right? So you're gonna grab your 100% and then you're gonna add it, or you're gonna grab your 100% and then you're gonna subtract. So because that one is a decimal, it would only make sense for your rate percentage to be converted to a decimal so that they can match, okay? Now, and then down here, we have obviously the keywords. This is not all inclusive. Obviously, there's a lot more keywords that we probably could find. I just tried to write as many as I could find, right? And just kind of like write them out without making it too expensive. Okay, so example 1. So Alexis bought a condominium for $83,000, assuming that its value will appreciate 6% per year. Write an equation that represents the exponential function. So notice in your notes, I literally write find, and then I'm giving you like an outline, right? So these are the things that you need to be finding. And if obviously you're not going to have this outline on an exam, you need to know that these are the things you need to look for. So the things we need to look for are the things that consist in the equation. So Alexis bought a condominium for $83,000. Do y'all know what a condominium is? No, a condo? Do y'all know what that is? Yeah, there you go. Which basically a fancy apartment that you actually own, right? So an apartment you don't own. You pay rent to the person that owns the building and you leave right after your contract. A condo is pretty much an apartment, if you ask me, but you're owning part of the building. So that chunk of the building is yours. Does that make sense? Kind of like a townhome. I don't know if y'all know what those are, but they're all kind of like around the same thing. It's part of the building that you own. Like a duplex, right? You know how a duplex is 2 houses put in one, but with 2 separate owners? It's the same concept, okay? So that's a condominium. Anyway, so this condo is $83,000. Assuming that its value will appreciate 6% per year, write an equation that represents the exponential function. So the difference between, I'm sure you noticed that it said per year, right? Which some of you might think, well, isn't that slope? No, you have to look at how it's growing. Am I going to grab 100% of what I have and then grow it? Or am I going to grow a specific number? So right here, Alexis bought a condominium for $83,000. So obviously this is my initial value, right? So 83,000, which I know is my A, right? Which I also know is my y-intercept. Now your growth and decay keyword, you can look at the words I gave you in the chart to kind of give you an idea of what to look for. In this example, we see the word appreciate. The word appreciate is the reason we know this is what type of function would this be? Would this be a growth or decay? Type it in the chat. So look at your table and look at your chart. Where do we see the word appreciate? Do we see it under growth or do we see it under decay? There you go. Right? So we see it right there, which is a growth word, right? And you should know from biology that DE means like down, right? Decrease, decrease, deny. If I deny you, that's a negative thing, right? Like that's not good. Decrease is not a good thing, right? DE. So anything with DE, you kind of already know that that's like down, decrease, okay? So we know that this is appreciate, which means it's a growth keyword. So that means that my rate is also going to be growth, right? Well, where is my rate? My rate is right here, 6%. And we should also know that if I'm given a percentage, I have to convert it to a decimal. So 6% is what as a decimal? Yes, 0.06. So because I know this says appreciate, I know that means this is growth, and I know I need to add in order to find my factor. So right here, you can see that I got the formula started for you, right? So I know right here, I need to have a plus because of the word appreciate, because that means growth. So I know I need to be adding. That says appreciate and then growth. I'm just pointing at it so that I know why I'm putting a plus. Now remember, your initial value is also your y-intercept, which is your A. And your A is what you started with, so 83,000. So we have what we started with, and then 1 plus whatever your rate is. Your rate is right here, so 0.06. Now, there's one thing I need y'all to understand. There is 2 different ways you can write this. If this is multiple choice, your answer could look like exactly what we just wrote, which is 83,000 times 1 plus 0.06 to the power of x. That is completely correct. Or it can be written in your factor form. So by that, I mean, instead of 1 plus 0.06, it could be simplified inside the parentheses. So if it's simplified inside our parentheses, then that means we have 1 plus 0.06 is what? What is 1 plus 0.06? Y'all have calculators. What is it? It looks like. What's 1 plus 0.06? There you go. So all you had to do was type it in your calculator, right? So this right here, 1 plus 0.06 is 1.06 to the power of x. And don't forget that you're multiplying times 83,000, and that is your function. Both of these are correct. I don't know what your multiple choice is going to look like, but you have to be able to simplify inside of the parentheses. What we also have is a way to check yourself. Okay, so what do I mean by that? So right here, right, this is your factor, which is your B. B equals factor. You know that if it's bigger than 1, it has to be growth. If it's smaller than 1, it has to be decay. You see the keyword appreciate. So you know that your factor has to be bigger than 1. Is 1.06 bigger than 1? Yes, it is. So then you know that this is correct. You know that that's probably right because 1.06 is bigger than 1. So we're good to go. So what do we know here? We know that our rate was 0.06, which is 6%. And because of that rate, it made my factor 1.06. We need to make sure we understand the difference between a rate and a factor. In order to have your factor, your rate has to be there. Okay, so for example 2, I'm gonna give y'all, let's go with 2 minutes to do that on your own, and then be ready to type the answers as I ask you to type them in. So 2 minutes, go. Good. So we have we know that the initial value is 500, and we know that the keyword is spends. And spends mean if you're spending something, that number's going down, right? Like you're spending something, so that's DK, which was also in your chart. So if we know it's DK, we know our factor when we're done, right, has to be 0 point something. Then lastly, our rate was 10%. So that 10% converted to a decimal was 0.1. Because we have DK, we know that DK means to go down, so we should be subtracting. And what are we going to subtract? Our rate, which is 0.1. And we're going to start with $500. So our function started at 500, and then we're going to decay, right, by a rate of 10%. Your factor is not 0.1, it is not 10%, that is your rate. In order to find your factor, you would have to simplify. So what is 1 minus 0.1? Go ahead and type that in the chat. What is 1 minus 0.1? What does that simplify to inside of your parentheses? What is 1 minus 0.1? You could just type this in the calculator, right? So I can see 2, 3 of you. So y'all got 0.9. Now, if you got, okay, so hold on, let me finish writing this. So inside my parentheses, right, 1 minus 0.1 is 0.9. And we have to the power of x, and don't forget your 500, right? So this is also, both of these are correct. Your answer choice could look like either one of these. Now, how can you check and verify that this is correct? How do you know that that's correct? Well, we know that it had to be DK, and we know DK, your factor is 0 point something. Your factor here is 0.9. Your rate is 0.1, which is 10%, right? So make sure we understand the difference between a rate and a factor. Your factor is what you get after you simplify inside the parentheses, so 0.9. And your rate is what you have to plug into the equation, so your percentage. Okay. All right, so that was example 2. So now, lastly, example 3. Oh no, the algebirds are endangered. Only 1/4 of the bird population survives each year. There are currently about 200,000 of these birds. Write a function that models the bird population. Okay, so what do we notice about example 3 in comparison to examples 1 and 2? Type it in the chat. So what do you notice about example 3 in comparison to examples 1 and 2 in the chat? What do we notice the differences? Okay, so a lot of us notice the same thing, that it gave us a fraction, but also that there's no rate, right? There's no percentage given. So if I didn't give you, if I'm not telling you, hey, it's by this percent, then that means you should not be using this equations right here. We should be using the ones at top, okay? How do I know? You know because it gave you a factor already. How do I know that's my factor? Oh no, the algebirds are endangered. Only 1/4 of the bird population survives each year. That means that you have 100% of your population and you're multiplying that by 1/4. So it's already giving you how many are surviving, how many are left over. So there are currently about 200,000 of these birds. So that means that this 200,000 is your initial value, right? So your A here, your initial which is what you start with, is 200,000. And that means that this 1/4 right there is your factor. Now, if we're saying that 1/4 of the bird population is surviving, if you have a chunk of birds and only 1/4 of them is surviving, do we have more birds or less birds than what we started with? So what is this? Would this be growth or decay? That's pretty much what I'm asking for. Is it growth or decay? Type it in the chat. Yeah, so we have that 1/4 survives, right? So this would be decay. And that makes sense because 1/4 is equal to 0.25. So your right, our equation is a times b to the power of x. Your a is always going to be your starting, which is 200,000. And then your b is your factor, which in this scenario, I already gave it to you, was 0.25, and then to the power of x. The other way you can write this is in a fraction, which would be 1/4 to the power of x. So both of these are correct, right? The only difference is that one is a decimal and the other one's a fraction. But it both means the same thing, right? Our factor is 1/4. Okay, so A, create a table that models the situation. Okay, so we know that our y-intercept is at 200,000. So that means that we started with this many, so nothing has happened, right? So X is years. So after 1 year, we're going to multiply by our factor, which is 1/4. So 200,000 times 1/4 or 0.25 means that after 1 year, we're only going to have 50,000 birds left. 50,000 algae birds. Multiply that again by 1/4. Then that means that after 2 years, we're going to have 12,500 algae birds. Why are they dying? Do y'all know why they're dying? Because y'all ain't coming in with your notes ready. That's why they're dying. You are the reason the algae birds are dying. Okay, moving on. After 3 years, again, our factor is 1/4. So multiply by 1/4, we have 3,125. I guess we have room for one more, so let's do it one more time. So that would be after 4 years, 781.25. But we're talking about birds here, right? So we can't have 0.25 birds. So we're gonna put 781 or 82. Either way, we're talking about birds. I guess I would put 82, whatever, same thing. Okay, so there's a table that models the situation. It makes sense, right? So we're multiplying by our factor every time. And I can see that my y values are getting smaller, which makes sense with what I came up with on the board problem. It's decaying, right? My population of birds is getting smaller, it's decreasing, and I can see that my table represents that. So B, based on the data from your table, what will be the population of the endangered bird at the end of 6 years? So after 6 years, how many birds are gonna be left if y'all don't have your outline ready the way you're supposed to? Well, it said based on the data from our table, right? So we could just keep going with the table, right? X, Y, after 5 and then 6. So we only need to do this 2 more times. So 781 times 0.25 or whatever we got the last time, it would be about 185 birds, and I'm approximating because it came out to a decimal. And then multiply that by 0.25 again. So then that would be 48.8, which is about 49 birdies. So after 6 years, there will be 49 birds left. They're dying, you guys, they're dying. Now, another way you could do this is that you could just grab the equation we found at the top and then plug it in. So we would have y equals 200,000 times 0.25 to the power of 6, because that's what we wanted after 6 years, and you would get the same answer of about 49. Okay, C, at what rate is the bird population decreasing? Notice that here it's asking for the rate, not the factor. So your rate is not 25%. That is wrong. That is your factor. That is what it's happening. The number you are multiplying by is your factor. So if you wanted to find your rate, well, the first thing you need to be able to acknowledge, right, is the fact that we already said this is decreasing. So in order to find our rate, well, where does the rate come from? What equation do we use to have the rate? Well, that would be f of x equals a times 1 minus r, because it said decreasing. So I know I have to be subtracting. Okay, so we already have an equation, right? We have f of x equals 200,000 times 0.25 to the power of x. So we can see here that this 0.25 came from somewhere. Where did it come from? It came from 1 minus r. So if I want to figure out the rate, all I have to do is have 0.25 equals 1 minus r. Right? That's where your factor comes from. Your factor comes from inside the parentheses. Inside the parentheses is 1 minus r. All I know is that that came out to my factor, which is 0.25. So subtract 1 from both sides. We have negative 0.75 equals negative r. Divide both sides by a negative 1. So we have an r equals 0.75. That means that your rate is 0.75, which is 75%. So these birds are decreasing at 75%. That's a big chunk. I should have made it not such a big chunk. Well, you see what happens for not having your outlines done? You're killing all the birds, all the algae birds. Poor birdies. Okay, so your factor in this scenario is 0.25, but your rate is 75%. Okay. So submit your notebook check, do your exit ticket. You have 20, 30, you have 18 minutes. That's enough time to get your exit ticket done. And then you can get started on lesson 31 outline. And lesson 32 outline is also in your modules and your table of contents. All right, let me